Okay, welcome everybody to the first meeting of the spring semester of the CUNY online set theory seminar. We are very pleased today to have Jing Zhang as our speaker. He's currently at the University of Toronto, and he's going to be speaking to us about highly connected Ramsey theory. Okay, take it away, Jing.
Thank you, Arthur. Thanks to the organizers for the invitation. I would love to visit New York at some point, but for now, it's on my screen. So the topic I'm going to talk about is some kind of variation of Ramsey theorem. So, and I'll explain the motivation behind why this is being considered. There are some connections of this kind of particular Ramsey theorem to algebra, homology, and also infinite combinatorics. But let me just set the ground of notation. I'm sure you've seen this many times, but I'll still repeat this. So lambda arrows kappa to nu abbreviates, for any f pairs of lambda into nu many colors, there is H subset of lambda such that the cardinality of H is kappa, such that F restricted to the pairs of H is constant. Okay, so this is the typical Ramsey theorem with the parameter lambda, kappa, and nu. Oh, and also if at any point, whatever I wrote is not readable, please let me know. Just interrupt me anytime. I am not the most confident about my writing, but I hope if I talk at the same time, maybe people can understand. So the classical theorem is the following, right? Omega to omega 2. Okay. Anyways, you can increase the arity. You can also increase the number of colors, but I'm just gonna write it like that. So this is due to Ramsey, right? And it turns out that Ramsey's theorem has a lot of applications. So naturally, people want to think about, there are problems that come up in infinite combinatorics that people want to solve. And, oftentimes people have a very, because of the usefulness of the Ramsey theorem in the countable setting. So it's natural that people want to generalize the Ramsey theorem to the uncountable in order to solve some problems in, topology, algebra, that kind of thing. But the problem is it's mostly false. So Sierpinski showed that you can't really generalize Ramsey's theorem to the continuum, for example, right? So this is just one of the many negative results that follow. A more dramatic failure is due to Todorovic, where you have the ultimate failure. Okay, so I'm not explaining this right. So this just, so there's a round bracket here. Let me just highlight this. This just means that whenever you give me, so there exists the coloring of pairs of omega 1 into, there exists the coloring of pairs of omega 1 into omega many colors, such that if you give me any subset of size aleph 1, then you actually see all the colors on the pairs of this set. Okay, so this is a very dramatic failure. So, and then we know that the next cardinal, such that the next kappa, such that the Ramsey theorem holds, is a large cardinal, right? So it's a well-known weakly compact cardinal. So now, suppose we have a very good argument from some version of Ramsey's theorem to derive a consequence in topology or, in algebra. It may be natural to feel hopeless, because what if if the version of Ramsey theorem you're using to derive the consequence is inconsistent, right? You can prove 0 equals 1, anything from it. So a natural thing is to look at weakenings of Ramsey theorems. Now, the weakening of Ramsey theorems has there are hopes that, maybe the Ramsey theorem, the generalization of Ramsey theorem at continuum or small. Sorry, let me close the door. The generalization of Ramsey theorem to small uncountable cardinals, like omega-2, omega-1 is not true, or continuum. But maybe, suitable weakenings, it could be true. Okay, so let's go to the central definition of this talk. So I wanted to keep the introduction short because I mean, we're talking about Ramsey's theorem. So the feature of problems in this area is that the statement is usually very short, and the solution may be a little bit involved, but then we're keeping the problem short, and it's also very easily understandable. So the central definition is the following. So this is due to Bergfolk, Rushak, and Scheller. So a graph VE is highly connected if the following is true. If you're given any subset of the vertices such that the collection of the subset you're given has cardinality strictly less than the size of the graph, then then if you remove this collection of vertices, the rest of the graph is still connected. So E is, okay, so the set of edges should be restricted to the remaining vertices. Is connected. Okay, so with this definition, well, first of all, let's see that the complete graph is always highly connected, right? Because I mean, any two vertices are connected, no matter how many. As long as you have two vertices left after you remove a set, it doesn't even matter if the cardinality is strictly less than the cardinality of the graph. The rest of the graph is always connected. Okay, so this notion is going to be central for the following variation of the Ramsey theorem. So this is again, okay, I'm gonna just, it's the same set of authors, so BHS. So lambda arrows, so we have a declaration here, highly connected. Kappa sup 2 nu, so abbreviates for any coloring, for any coloring F on pairs of lambda into nu many colors. There is a set of lambda, it's a subset of lambda such that H has cardinality kappa, and a popular color I nu, such that H and the inverse image, right? So the edges that has this popular color is the highly kinetic graph. Graph. Okay. Is there any question about the definition? I'm gonna draw a picture actually to just illustrate why this is a weakening, and what are we weakening? What exactly are we weakening? So maybe let me do that. Sorry, I'm gonna open the door. they're very bad at conserving energy. The indoor is like 35 degrees Celsius, so I'm extremely hot. Uh, uh, okay, so sorry. So roughly speaking, in the conclusion of the Ramsey theorem, we are looking for a clique, right? So we're looking for a monochromatic clique. So let's say here we're doing an illustration. Let's say the goal is to get a 4 clique. So we're getting a complete graph of size 4. So between any two, and all of them are of some popular color. So this is the usual conclusion of the Ramsey theorem. Now, roughly speaking, this new partition relation is asserting the existence of the following. You want to have still 4 vertices, except that they're not necessarily clique. So but again, between any 2 vertices, there's some connection between them. So the replacement is the following. I'm replacing the clique by some path between them, right? So between any 2 vertices, they're still connected. I'm oversimplifying actually. Or maybe I should use color. I'm oversimplifying, but this is roughly the idea. So you're replacing the edges by a path, but then also you want the path to be monochromatic. So all of these are of color I, right? And between and you need to replace edges with path, and replace monochromatic edges with monochromatic paths. So that's the intuition. If you look at the definition, it says a little bit more, right? It says that not only you can find, between 2 vertices, not only you can find a monochromatic path between them, you can actually find many. So this is reflected in the highly, this highly here is saying that you can actually find between any 2 vertices, you can find many monochromatic paths that connects the 2 vertices. Okay, so that's the idea. And it's clear that this is a weakening of Ramsey's theorem, right? So with this picture, I believe I'm gonna draw a lot of picture today, just because I guess Ramsey theory is also nice in the way that you can explain by drawing pictures. If you have the stronger Ramsey theorem, then trivially you have the weaker one, just by the fact that an edge is a path between the 2 vertices. Okay, so so now we have a candidate of. Okay, so before I talk about where these partition relations come from, or like some recent applications, let me just give a very okay, I have let's give a simple observation just to get ourselves familiar with what this is all about. So the observation is that for any cardinal kappa, okay, let's say greater or equal to omega, and for any finite r, so kappa arrows HC kappa R2. So this is basically saying that this is if you're only concerned about finitely many colors, and this is a truly weakening of the Ramsey theorem, because I mean the corresponding Ramsey theorem, I mean if the analog Ramsey statement of this is just false, right? Because of Sierpinski's result, Tadashevich's result, but then here is, if you're only concerned about finite colors, this is actually a consequence of, it's provable in CFC. And the way that you do this is actually very easy. So let's just see this quickly. So fix a uniform ultrafilter U on kappa. So here I just mean I just mean that any large set, any set in this ultrafilter has cardinality kappa. And you can easily construct such an ultrafilter by the X. So using axial choice. And then given a coloring on pairs of kappa into R many colors. So we just do the usual thing as we would prove Ramsey theorem. So for each alpha less than kappa, let's just try to find a popular color. Find I alpha in R such that A alpha equals beta, such that C of alpha beta equals I alpha. This set is popular, right? You're only decomposing the whole space into finitely many pieces, and one of those pieces has to lie in the ultrafilter. And then you just have to uniform. Okay, so just find A in U such that, and also I in R such that for any alpha in A, I alpha equals I. Then A and the preimage of I, this is highly connected. Right. So why is that? If you're given, so let's draw another picture. What this is saying is that you have found this A such that if you give me any 2 points here, I can find something that's large enough, say gamma, such that they're both connected to gamma. But also the edge, both of the edges would have color I. So you essentially just replace each edge in the conclusion of the Ramsey theorem by a path of length 2. Okay, so this is the first contrast, easy observation. So it should be clear that the difficulty will come in when the number of colors is increased, right? So if we're not only thinking about finitely many colors, if we think about countably many colors, then it's not clear, because whenever you have a countably complete ultrafilter, you're automatically, I mean, itself may not be a large cardinal, but there exists some large cardinals below kappa. So that causes some difficulty. Okay, so let me say we're gonna focus on the scenario where the number of colors is omega. Okay. So let me just, before I mention the main result, let me just mention a few recent applications and also motivations, regarding why people think about these partition relations, motivations, and recent and applications. So the first one, so I'm just going to mention 2. Supposedly there are a lot more, but yeah, I only have limited number of time. So it's the Bannister, Bergfolk, and Moore, Tadachevich. So they use apply a partition relation, so the partition relation in the family to study a problem in in homology. So I'm actually not sure what the original homology question was. I only knew about the combinatorial reformulation. So let's say this problem. Okay, so let me say the Ramsey property that they come up with is called PHN kappa. So PH stands for partition hypothesis, and kappa is the source cardinal, as you would expect, and n is the dimension. So n is a natural number. So their Ramsey property is also a weakening of the Ramsey problem, and also they replace monochromatic edge by monochromatic path, but of length 2. So this is not exactly the highly connected Ramsey theorem that I was talking about, but it sort of falls into the family. And this kind of partition relation was used to establish what is called the simultaneous vanishing of higher derived limits. I'm not going to define that, but basically the one-dimensional theorem is equivalent to a certain compactness statement about, if you have an object such that any object of smaller cardinality is trivial, then the big object has to be trivial as well. I'm not defining anything, but I'm just okay. So this is just mentioning one of the recent use. Actually, let me just say this instance, right? Kappa is somehow related to what we're studying. So let me just write it out what this means. This is saying that for any omega coloring of pairs of kappa, there exists a subset of A such that cardinality is full, such that for any alpha less than beta in A, there exists the gamma greater than beta such that, oh, I must fix a popular color as well, such that C of alpha gamma equals C of beta gamma equals I. So in picture, it's just saying that the goal is to try to find a popular A and to find a popular color I, such that whenever you have two guys inside, they're connected in the future by some, via some edges of the popular color. So this is very much like the conclusion of the proof that I just gave, except that I only use finitely many colors. And you can just use uniform ultrafilter because they're always close on the finitely many unions or intersections. So intersections.
And just a second, in what you did, you could also require that this gamma is an A, right? While here it's not required to be an A.
Yeah, yes, exactly.
Yeah, right.
That was exactly the point that I'm gonna bring out. So they don't require, in the application that they need, they don't need this gamma to be an A. So in general, requiring this gamma to be an A is a little bit more difficult than not.
Right.
Yeah. So it looks like the partition relation that we're investigating, but not quite. But of the similar spirits, by replacing monochromatic edges by monochromatic paths. And the second application, is there any other question?
Can you so with Ramsey's theory, are you coloring the edges or the vertices?
Coloring edges.
Yeah, so what's a monochromatic edge?
What's a monochromatic edge? Wait, I'm sorry, I didn't hear you.
Yeah, because you're saying a monochromatic edge.
Oh, right. That's what I mean is just all the edges of a popular color. So in all of the conclusion, I have a popular color. So that was probably I said something that doesn't make sense. When I said monochromatic edge, I just means that the edge of the specified popular color.
Oh, okay, okay. Interesting.
Yeah, sorry.
Yeah, I don't think you said it wrong, but so I think the idea is that there can be a monochromatic set of edges, right? Not a single edge can't be monochromatic. It just means that all the things in the set get the same color.
Exactly. I should say that the edge is in the monochromatic set of edges, instead of saying that it's a monochromatic edge.
Yeah, it makes sense now. Okay.
Okay, so the second motivation, this is regarding separating two combinatorial notions at an inaccessible cardinal. So let's just recall this. This is when kappa is uncountable. This is precisely characterizing weakly compact cardinals, right? Is inaccessible. Okay, strongly inaccessible. And there is no kappa Aaron geometry. And it's a long-standing question whether for inaccessible kappa, having no kappa Aaron geometry is the same as having no kappa Suslin tree. Right, so we know that if we go to omega 1, then they're different. I mean, omega 1, there's always omega 2. So if you don't talk about inaccessible cardinals, then these two notions can be distinguished. But at inaccessible cardinals, just I guess it's probably due to lack of technology. At the moment, we're not able to distinguish. We're not able to exhibit a model where these properties are separated. Of course, if you don't have kappa Aaron geometry, then you don't have kappa Suslin tree. So it's the other direction. Can you get a model where there's no kappa Suslin tree, but there's still some kappa Aaron geometry? But so how is this connected to this weakening, this family of weakenings of Ramsey theorem that I'm talking about? It's a recent theorem of Comia and Schiller. They prove that if kappa is regular, the kappa arrows kappa topological copy of kappa kappa. I'll explain what this means. If and only if there is no kappa Suslin tree. So this is the it's the first step towards the approximation. So this is, if I'm trying to prove a positive result, you better have a characterization of no kappa Suslin tree in terms of the partition relation. So there must be, but this is weaker. So let me explain. So here, it says that for any f, okay, let me write it on the right-hand side. So this is IE for any f coloring pairs of kappa into two colors. Either there is H subset of kappa, H of size kappa, such that f is monochromatically 0 on the set, or okay, there is a topological copy. I'll draw a graph because if I'm trying to write out definition, I'm gonna spend a lot of time of kappa, k kappa of color 1. So basically, a topological copy of this k kappa is just the following. You have kappa many vertices, right? And then for between any two of these vertices, there exists a path. Again, we have to talk about path all the time, connecting them. And you want all of these paths that participate, in connecting these vertices are disjoint, except for the endpoints. So like that. And a requirement is that all of these guys will have color 1. So all of these have color 1. So this is exactly what the kind of illustration that I did when I introduced the partition relation. So it's kind of it's almost k kappa, but modulo some contracting. So okay. Cool. Is there any question? Okay, so let's go back to, I guess I've given enough background so I can state the theorems. So back to lambda arrows HC kappa nu 2. So let me first say what's already known. So 1, okay, 1, 2, 3 are due to the author that I just cited. So Bergfolk, Rushok, and Sherlock. And so the first observation is that 2 to the omega doesn't arrow 2 to the omega 2. And this is just, you can also say that this is due to Sierpinski. I mean, the Sierpinski coloring would work. Sierpinski coloring would work. So we are thinking about coloring with omega many colors here. So I forgot the HC. The partition relation for continuum is still not true. But then there's some. This is sharp in a lot of sense. So you can prove. So the following results that I'm gonna say are suggesting that this result is sharp in various senses. So if you assume that the consistency of a weakly compact cardinal, you can get the consistency of 2 to the omega 1. Okay, arrows 2 to the omega 1, omega 2, HC. If I forget about HC at some point, please interrupt me because I tend to forget about this index a lot. So what this is saying that the previous theorem is sharp in the sense that if we don't think about the continuum, but instead we think about the power set of 2 to the omega 1, then it's possible that this is true. Actually, the third one is not due to them. So the third one is due to Chris Lambie Hansen. So he proved that the first result is also sharp in the following sense. Assuming the consistency of weakly compact cardinal, you can get the consistency of 2 to the omega arrow. Let me explain what this means. You can't get it to be monochromatic, but you can kind of reduce it to 2 colors. So start with omega coloring of the edges of 2 to the omega. And what I'm claiming is that I can't really find a highly connected subgraph such that it is monochromatic. There's a popular color connecting these edges. But what I can do now is that I can reduce it to 2 colors. So start with omega many colors. Now I can reduce it to 2 colors. Let's say maybe only color 5 and 3 would appear in this graph. So that's also another way of saying that the first result is sharp. Chris also showed that actually the reverse is also true, right? So he also showed that the large cardinal hypothesis that he used is actually necessary. So it's an equiconsistency result. So there's another way of asking if the theorem, the Sierpinski theorem, is sharp. And this is, let's go to the questions asked by these authors in their papers. The Bergfolk, Rusha, and Sherlock asked the following question. So what is the least new such that new HC nu to omega can hold? Let's say consistently. So a typical, a few particular cardinals that they listed was omega 2, Aleph omega plus 1, you know, these. I should mention that in both of these theorems, right? So in this theorem, 2 to omega 1 is large. So it's a former weakly compact cardinal. And in Chris' result, 2 to the omega is also a former large cardinal. So they are not large in the sense of cardinal exponentiation, but they're large in the sense of absoluteness. Like it's not Aleph n for any n. It's a cardinal fixed point. So their question is about, can we have a more let's say have a more definable smaller cardinal such that this partition relation is true, it's consistently true. There, of course, it can't just be true because of Chris's result. It implies the failure of square. So, and the second question is, okay, so the second question I probably have less time to talk about, but they ask if CH is equivalent to this omega 2. Now, why is this a natural question? Because CH is actually equivalent to the Ramsey version, right? This is without HC. Without HC, this is just Eldeshirado. And you can prove that this instance of Eldeshirado is actually equivalent to CH. So the natural question is that whether this particular weakening or a formal weakening of the consequence of the partition relation is actually equivalent to CH. So the theorem is just to answer all these questions. So let's see. Let me write down yes and no. Okay, so it's possible to get nu to be omega 2, Aleph omega 1 plus 1, and CH is not equivalent. So let me write down the hypothesis that I need. So if we start with the measurable, then we get the forcing extension such that the highly connected Ramsey theorem at Aleph 2 is true. Actually, yeah, so all of these, I don't know if this is a bad habit, but all of these guys involved are cardinals. So I probably should have written it as Aleph 2 instead of omega 2, but you get the idea. And if you assume more, right? So that's just for Aleph 2, but what if you want more? So if you assume the existence relative to the consistency of a super compact cardinal, then you can get all of them. So the conclusion is for any kappa greater or equal to omega 2, kappa irregular, you have this. So of course, in this very strong model, you will have everything, omega 2, Aleph, omega plus 1. But let me just say something about the use of the hypothesis here. Oh, maybe let me finish. Let me finish. Okay, so the last one, I don't think I have time today to go over to state exactly what the large cardinal hypothesis that I need. So I'm just gonna write large cardinal. Implies the consistency of not CH and omega 2 HC, omega 1, omega 2. Okay. So the hypothesis here is, I guess, in the modern perspective, is or like currently is kind of inevitable, and the reason is just because let's say if you have, so this is Chris Lambie-Hansen's result. If you have Aleph omega plus 1 HC arrows, Aleph omega plus 1 to omega, then square sub Aleph omega must fail. Okay, so we know that, you know, there's some very non-trivial large cardinal strength, you know, maybe in the verge of what we currently understand. So so super compact is just not there for convenience. There's some inherent need to use that. Okay, so this is so I'm gonna say a few words about, so I'm just gonna concentrate on the first theorem here. So the idea, so I'm trying to illustrate some idea of proving Ramsey's theorems using ideal hypothesis. So so usually if you have large cardinals, then, you know, it's a natural generalization of just cardinals satisfying Ramsey properties. So you can kind of lift the corresponding Ramsey results very easily to large cardinals. But now here we are doing something not based on ultrafilters. We're doing something based on ideals. So those are usually, let's say, broken or generic large cardinals. They usually arise after you collapse a large cardinal to something that's more manageable. And it's many of these theorems that to prove it, it's not just looking at the generic points in the elementary embedding. There's some kind of genuine combinatorics that go into prove some of these theorems, and sometimes a little bit tricky. So let me just try to illustrate the green box here, and I think that's what I'm going to do for the rest of the talk. Is there any question? Okay, so the assumption, let me give you the assumption. Assumption is that, okay, so again, let me remind you of the goal. So the goal is to sketch the proof of omega 2 arrows, omega 2 to omega, right? And we need some assumption. Assume I is a complete ideal. Oh, also uniform ideal on omega 2, and D is a collection of positive subsets, is dense, and countably close. So the first part is the standard assumption. You want to have an ideal that's countably complete, but it's also uniform. So it just means that all the elements, so it contains all the elements of small size. Anything that's not in the ideal must have the full size, which is olive 2. And it's also, now the second requirement here is a little bit, it's a little bit unusual, but let me explain what it means. It just means that you have a collection of dense subsets. So dense in the sense of containment mod I. Okay, so all the order I'm talking about here is containment mod I. So if you have a collection of subset that's a collection of positive sets such that it's dense, right? So any positive set, you can have a positive subset mod I in this collection, such that this collection is also countably close. So this kind of ideal is you can easily get it from such forcing extension. So just do the Levy collapse, collapsing the measurable cardinal to omega 2, then you get such an ideal. To prove that there exists a dense subset that's countably close, the proof is originally due to labor. Okay, so okay, so let's see how this kind of the existence of such ideal can help in proving our Ramsey theorem. So recall that we are given a coloring on pairs of omega 2 into countably many colors, and now we're trying to find a large subset, right? A large subset, aka a set of full size, such that, and also we try to find a popular color, such that the graph on this popular full size set is actually highly connected. So let me give a definition, and then I'll give a lemma, and then the final proof of this is just to iterate the lemma countably many times. And I think it would be very instructive to illustrate this with pictures. So I'll try to draw as many pictures as possible. So given two positive sets, B0, B1, and a color I, we say B0, Bi, B1, I'm sorry, is I frequent. Okay, so I frequent. If I explain why, where this comes from, for any further positive B0 prime, for any further positive positive B1 prime in B1, you have, it is the case that the edges that gets color I is kind of positive in the Fubini product of these ideals, of the ideal. So what I mean is the following: B1 prime such that C of alpha beta equals I is positive, and the outside set is also positive. Okay, so what's the intuition? The intuition is that when you say B0, B1 is I frequent, it must mean that there are many, many I edges going from B0 to B1. So you wanted to express something like, okay, let me draw a picture here. So you wanted to express that you have B0, you have B1, and you have many edges of color I that goes in between B0 and B1. This is what you want to express. But as in, in Ramsey theory, we need to have a dense, in order to prove Ramsey theorems, sometimes one step is not enough. That's why there's some kind of density thing here. You sort of want this frequentness to happen very inherently. So let's draw what it means, right? So what it means is the following. Suppose you're given B0, you're given B1, and then we say it's I frequent, so I is given. It means that whenever you shrink to a positive subset, B0 prime, and you shrink to a positive subset of B1 prime, you can find, okay, after you shrink, now however you shrink, you can still find many edges going from I0 prime to I1 prime. And the many is expressed in terms of, positive, in terms of the Fubini product of this, of the ideal. Okay, so I hope this okay. I hope this makes a little bit of sense. So why do we want this definition? So the point of having this definition is to find lots of positive sets that are I frequent. So it's only natural, because if you think about two positive sets as I frequent, that just means there are many edges with color I going between them. And if we're trying to build a monochromatic path, that's only a good thing. So we need to prove existence. So the lemma is that there exists B, a positive set, exists I, a popular color, such that any positive B prime subset of B, there are positive B0, B1 subset of B prime, such that B0, B prime, I'm sorry, B0, B1 is I frequent. Okay, so let me draw again. So that's not write any proof, right? So what this is saying that I'm able to find a positive set, and I'm also able to find a popular color, such that whenever I shrink, right, this is given by you. You give me a positive subset of the B. If B prime is positive, then I'm always able to split this into two parts, B0. When I say split, I don't really quite mean splitting, like they don't have to be disjoint. But I think this is a good way to visualize. I can always split them into B0 and B1. Okay, not very accurate about drawing. I can always split them into B0 and B1 such that they are I frequent. So I have many edges connecting these two parts of color I. So that's just the point of what this lemma is saying. And I would so the proof of this lemma is by the usual exhaustion argument. We have to use two things, right? We have to use the fact that this ideal is sigma complete, but we also have to use that it has a sigma closed dense subset. So that means that imagine how you would prove this lemma. You would say, oh, suppose this is not true. Then for any positive set, you can find a positive subset such that, okay, for any positive set, for any color in omega, you can find a positive subset such that something happens. But then, that the collection of positive sets is countably close. So you can go through this process omega many times, and eventually you're going to reach a contradiction, because essentially all the colors would be bad after you diagonalize this omega many times. So it's an exhaustion argument. So I hope, okay, so this is the first step of the proof, and the second step is just to iterate, right? So the second step is to iterate this lemma many times, omega many times. Omega many times. You should always think about this picture. So the first step of the construction is to have find a sequence of positive sets such that for any n less than k, it is the case that Bn and Bk is I frequent. Okay, so this is the first step. And how do we do that? So you can see that in the previous lemma is essentially a splitting process, right? So this let me say this, you found this B is some kind of a positive, it's a local thing that you want to work within from now on, because you have obtained your popular color. But the property of working within this B is that whenever you have a positive set, I'm able to split them into two positive sets such that they're I frequent. Okay, so now it's rather clear. Let me draw another picture here. What you should do to find this, right? So you start with B. Now, because of the previous lemma, we can split them into B0. Okay. We can split them into B0 and B0 prime, such B0 prime. I'm not using B1 because I'm going to use B1 for the next thing, such that these guys are I frequent. So you can always do that, right? But now you repeat the same process to B0 prime, right? Because recall that the previous lemma, this is asserting that you can split for any positive subset. So what you do here is that you split again B0 prime, and you get B1 prime. I'm sorry, B1 and B1 prime, such that they are I frequent, right? And then you continue, and you keep splitting, and you get B2 prime, and they are I frequent. And then you can get B0 and B1. So in the end, this row is what we're interested in. This is exactly what we get. This being I frequent is inherent. Is if B0 and B1 are, if they're I frequent, then if you go to any positive subset, they're also I frequent. Because remember, being I frequent is we're saying there's a for all quantifier. We say for all positive subsets, something is true. And okay, so right. So the second step is just to shrink. So Bn to Bn star, such that okay. Such that for all k greater than n, right, we have and also for all alpha in Bn star, it's the case that beta in Bk, C of alpha beta of color I is I positive. So this is also not too bad. This is basically, we can do this just because all of these pairs are I frequent. So you can just throw away the null set that you don't want to consider. And So the conclusion, okay, I'm gonna write it here and draw another picture. So finally, B star N, the union of this is highly connected. Highly connected witness by color I. Okay, so let me draw another picture to illustrate what I'm doing here. So after the first step, I have a bunch of blocks of positive sets. So B0 star, B1 star. So I have omega many blocks. So what I make sure is the following. So let me say this is BK plus 1 star. So if I'm given any alpha and beta here, what I make sure is that there are actually many guys. So there are many guys here that has color I with alpha. So this is what I make sure. And then it's actually saying for all the K that's greater than, the block alpha is in. And the same thing for beta in the next block, right? So all of these, sorry. All of these, okay, if I draw, by now you should probably know I'm a terrible guy to draw. In BK star, there are positive many sets that has color I with alpha. And in K plus 1 star, there are positive many things that gets color I along with beta. But then we finally we know that this pair, BK star and BK plus 1 star, is I frequent. So in the end, you're able to find from these two positive sets another edge connecting them of color I. So in the end, you can connect from alpha to beta via a path of length 3. So let me just write it out here. You have alpha here, and you connect to, let's say, alpha 1. This is from BK star. And then you connect to alpha 2 in BK plus 1 star. And then you connect back to beta. So 1, 3, so path of length 3 of color I. Okay, so that's the idea of how the proof goes. I hope it's not too sketchy. It must be very sketchy, but at least if you see the picture, it kind of makes sense. Why I'm doing this. But there's one immediate question. If nobody's gonna ask, I would just ask, why don't we do something as in the finitely many color case? So basically saying that, why don't we just reach beta in 2 steps, right? So alpha goes somewhere in the future of color I and then come back to beta. We can't do that. So it's, let me just write a remark here. It is consistent with the ideal hypothesis. So when I said the ideal hypothesis, it's the ideal hypothesis that I derived this theorem from, that omega 2 does not arrow omega 2 to omega via path of length 2. So I need path of length 3, and it's optimal using this ideal hypothesis. So this brings us to the questions. So I'm gonna just So the first question is exactly what if we strengthen the hypothesis, can we get the stronger form of this partition relation where you require the paths of length to be exactly 2 or less or equal to 2. So is omega 2 arrows. Okay, so I'm gonna highly connected less than 3, omega 2, 2, omega consistent. So 3 here is saying the path should have length less than 3. Okay, and so this is relative to any large cardinal assumption. I don't care. So in general, another class of question is can we separate the following: omega 2 arrow HC less than n, omega 2, omega 2. So this is again, this is saying that the witness of the highly connectedness of the graph should have all the paths of length less than n from omega 2 HC less than n, omega 2 for different n and m less or equal to omega, right? So does it make difference? I mean, in the case of 3 and 2, there are models that distinguish them. But what about other values of n and m? And so finally, the third question is, can we do it with a weakly compact? For some reason, there's some annoying technicalities, but I obviously didn't try to optimize this. If we get this, it would be equiconsistency, right? So we use a measurable for this, but what about just using a weakly compact? I guess that's everything I have.
Thank you. That was a great talk. Very nice. Thank you so much.
Good night, Jing.
Thank you.
Yeah, you already asked a lot of questions yourself.
Sorry.
Are there any further questions?
I had a small question. When you those 3 theorems that you had, I know you focused on the first one, but on the third one that said consistency of some large cardinal.
Yes.
Implies consistency of not CH. I was just wondering, how big is the continuum there?
It is it can be as large as you like. So yeah, let me think about this. It's okay, it's a certain omega 1 carrying a saturated ideal. So in this theorem is saying that there is an ideal on omega 2. But because in the other theorem, we're trying to find a highly connected subgraph of size Aleph1, you need the ideal to be on omega 1. And in that case, you can essentially achieve any large, like however large continuum you like. So just consistency results of saturated ideal on Aleph1, but with large continuum. And the saturation property you need is something like omega 2 Naster. Usually when you talk about saturated ideal on omega 1, you want omega 2 CC, right? Omega 2 saturated. But then here I need something that's a little bit stronger. I need omega 2 Naster. Whenever you have omega 2 many positive sets, you should be able to find an omega 2 subset such that any 2 are compatible, intersect to be a positive set.
Okay.
Yeah.
All right, makes sense. I'm sorry, we have another seminar in a few
Yeah.
minutes over here.
Yeah,
I don't mean to cut it short. But
No. You're supposed to start earlier, right? So I couldn't. I was teaching, so
Yeah.
All right.
Okay. All right. Well, thanks again for this awesome talk. Really good use also of the whiteboard. Exactly the right topic for that. Okay. And
you.
everybody have a nice weekend. See you next week.
Till next week. Thanks again.
Bye. Have a nice weekend.
Bye.